Today, in this recording, I'm going to talk about the solution for the problem heaps find the running median. The problem description, we can start from here. Given an input stream of n integers, you must perform the following task for each ith integer. Add the ith integer to a running list of integers. Find the median of the updated list, and then print the list's updated median on the new line. The constraint A is larger than or equal to 1 or smaller than or equal to 10 to the fifth power, and AI is larger than or equal to 0 or smaller than or equal to 10 to the fifth power. Here is an simple 6 is means we are going to add 6 integers sequentially, and the following is 6 integers. For each time when we add an integer to the list, we calculate the median and print it out. For example, the first integer added is 12, so the median is 12. The second element added is 4. In order to add a median, first we need to sort the list and then we get a median. Since the size of the list is even, so the median would be the average of the two middle values. And then we add 5. And we sort the list, and since the size is an odd number, the median would be the middle value, which is 5. And then we add 3, we add 8, and we add 7, and we get the median with the same way. As you can say, the most straightforward solution would be we maintain a list each time we append our new integers to the list, and then we sort it, and then we get a median. So let's look at the time complexity. We add, we sort. If we add one integer, the sort, we can use the quick sort. The most efficient way would be log n, and then we get a median. That would be O1. It's constant time complexity. So when we add one integer, we just need to sort one integer. So time complexity would be 1 log 1, and when we keep adding, time complexity would be number of the size of the list, and the log, and the log if the size is k, so time complexity of the sort would be k log k, until we add all the n integers to the list. So that would be this. So as you can say, the time complexity of this method is larger than n log n, and if we replace all the log with log n, so that would be smaller than 1 plus 2 plus n. Estimated time complexity would be square of n log n. So as you can say, this method, the time complexity is between n log n and square n log n. This is not very efficient. So let's think about some other way to do that. So let's take an example. For this array, the median is 6. So in order to get a median, we can maybe divide the array in two parts, the left part and the right part. So the 6 is a maximum value on the left part. If the size is even, we still divide the list in two parts, and the median would be 6 plus 7 divided by 2. So that would be the maximum value of the left side and the minimum value of the right side. So this one is max. So what we are going to do is we can just get the maximum value and the minimum value from the left side and the right side. So what data structure can you think of about this? It is a heap, right? For the left side, we can use a max heap to maintain it, and for the right side, we can use a min heap to maintain it. So if the size is a odd number, so the median would be max heap dot peak. Of course, you can also include the median into the min heap, but in this example, I'm going to include the median into our max heap. And for this one, the median would be max heap peak plus min heap peak divided by 2. So how can we maybe maintain the list? Let's say if on the left side is A1, A2 to AN, and the right side Bn, Bn minus 1 to B1. If the size is the odd number, which means n equals n plus 1. And on the left, we use the max heap. Right side, we use the min heap. Currently, the median is a max heap dot peak. The top integers are in the max heap. Since An is a median, which means all of the elements on the right side is larger than the left side. So when we add a new element, for example, if we add k, I'll just first add it into the max heap. You can choose either side. I choose to add it to the max heap. So that the size of the max heap would be n plus 1, and this is it has two more elements than the left side than the right side. In order to get a median, we have to transfer one integer from the left side to the right side. Since all of the elements on the right side is larger than the left side, we need to transfer the maximum number from the left side to the right side. Likely, we are using the max heap, so we just pour our max value and add it to the min heap. So yeah, currently the size is balanced, and all of the elements on the left is larger than the right, so we can get our median is the max heap the average of the top integers of the max heap and the min heap. If the size is even at first, that which means n equals to m, so the median is an plus bm divided by 2. If we have the k, first I'm going to add it to the min heap, max heap. Alright, so the size of the left is m plus 1 and the size on the left is n. So it's okay, yeah. Currently the size is fine, so can we just get a median by the max heap topic? You cannot because we are not sure the value of k, right? If it is smaller than an, or we can just insert it here, yeah. Then we get a median an, yeah, that's okay. But if it is larger than an, but smaller than bm, so like here, yeah, the median would be k, so we can still use the max heap topic to get it, it's fine. But if k is larger than bm, if we add it into the max heap, the k would be larger than the bm, so yeah, then the list will be out of order because all of the values in the right side should be larger than the left side. So what we are going to do is we pour the maximum value and add it into the min heap. So inside the min heap, all of the elements will reorder, and we can just get the mean value back to the max heap, so that currently all of the values inside of the min heap is larger than the max heap, so we can just use the max heap topic to get our median. Next we can write our code. So we have we can use a priority queue. We have the max heap be integer. Max heap, the natural order is a min heap. For the max heap, we need to reverse the order. So we can use a collection store reverse order. Okay. And then we declare our min heap. Yeah, it's just something like this. So we have our array A, and for example, A for each time we add one element, so I is smaller than A length. So each time we add a, first I'll add it to the max heap, so it will be added to the left side. AI. If the size is if current the before adding the AI, if the size is an odd number, we after adding, the left side has two more elements than the right side, so we need to transfer one to our min heap. So we will going to transfer the maximum value from the left side. So we offer the max heap to pour. We pour the max value and add it to the min heap. Okay. Currently, the size is okay. Both sides are equal to each other, and the median it would be the average of the top of the two heap. If the size is an odd number, it is an even number before adding, and when we add AI to the left side, but we are not sure if AI the range of the AI, it may be small, it may be just fit into the left side, but it may be belong to the it maybe have belong to the left side, right side. So what we are going to do is we pour the maximum value and we add it into the min heap and we get the minimum value. Yeah, it's like a swap the maximum value on the left side with the minimum value of the right side. So this means when we add AI, the size of the max heap is larger than the min heap. So we add AI, we pour, and we add this. We pour and we add it to the max heap, min heap. Currently, the min heap has one element larger than the left side. So if the min heap size is larger than the max heap size, we need to maybe get the minimum value back. So max heap min heap dot pour. Yeah, so that way, so that the array is in order. So if so that we can get a median if after adding, if the number is a median, if the size is an even number, so that the min heap size is equal to the max heap size. We can get our median. The median. I'm going to define a list for our median. Integer median. equals new array list. So median dot add. Yes, it's even number, so that would be the mean heap dot pick plus max heap dot pick and then divided by 2.0. Median we will use a double data type for the median because the median may be since we are divided by 2, then maybe not integer. Else if the mean heap size is not equal to max heap size, which means currently the size is an odd number. In my example, I always include the actual number inside of the max heap, so I just add the top of the max heap to the medians. Heap dot pick. Here maybe I'm going to use a double, and here I'm going to force it to double data type. Right, here we have a code. That's it.